Welcome everyone. In this video, I'll walk you through the different data types and sizes in GPUs. But let me tell you something here. Understanding data types and sizes is like choosing the right tool in a toolbox. It's fundamental to achieving the task efficiently and accurately. In the world of GPU computing, and just like in CPUs, we have different ways to store numerical values depending on our needs. For example, let's start with the integer numbers. For integers, we can use 8, 16, 32, or even 64 bits. The more bits you have, the larger number you can store. For example, an 8-bit integer can store values between 0 and 255 if it is unsigned, or from minus 127 to 128 if the variable is declared as signed. For a 64-bit integer, we can store much larger numbers, up to like 18 quintillion. Now, when it comes to numbers with the decimal point, we use floating point representations. These numbers also come in different sizes. For example, we have the 16 bits, which is known as half precision. Then we have the 32 bits, and this is known as the single precision. And finally, we have the 64 bits, and this one is known as double precision. In C or CUDA programming languages, declaring a variable with int uses 32 bits. And if we replace int with long, then this is often uses 64 bits in the memory. Similarly, on the other side, if we declare a variable with the float, then we use 32 bits in the memory. But if we replace float with double, then we use 64 bits in the memory. Half precision. This is a binary floating point format that occupies 16 bits or 2 bytes in the computer memory. It is also known as FP16. 16 here refers to the 16 bits, and FP refers to the floating point term. Half precision offers lower numerical accuracy but requires less computational resources, and this makes the half precision suitable for specific applications such as machine learning and graphic processing where high precision may not be necessary. Single precision is also known as FP32, and again 32 here refers to the number of bits required to store this type of variable, and FP refers to the floating point. This type offers a middle ground between the speed and the accuracy, and this is why the single precision is the go-to choice for a wide range of computing tasks. Then we have the double precision or the FP64 type. This type is considered the precision powerhouse, and this is because scientific computing and complex simulations where every decimal point can lead to a butterfly effect rely on this type, rely on the FP64 precision. This type ensures that simulations of phenomena like climate patterns or molecular structures are close to reality as possible. This approach and these different levels enable GPUs to be adaptable and utilized in a wide range of industries and applications. That's why in one of the research papers that investigated various GPU data types, it was discovered that double precision calculations require 4 execution cycles. But the single precision computations consume only 2 cycles, which indicates that the double precision is lower but provides higher accuracy. For example, if we have this code here, let's say float x, y, and z. And let's start with x equal to 10.3 and y equal to 5.8. And we have an instruction or operation in which z is equal to x plus y. then this operation will take only 2 cycles to complete. However, if we replace the float type with double, the same operation, the addition here, requires 4 cycles to complete. This change in cycle count is due to the increased precision and processing requirements of the double data type. To clarify more, let's examine how the number pi is represented in different floating point precisions. In half precision format, the pi number is represented with just 2 digits following the decimal point. This increases to 7 digits in the single precision format and further extends to 15 digits in the double precision format. That's why the double precision is chosen when high accuracy is required. This implies that for a small number like this number here, this number cannot be accurately represented in half precision format. It would effectively be approximated as 0. This limitation arises because half precision only supports up to 2 or 3 digits after the decimal point, and this is why the half precision is unsuitable for representing such fine-grained values.